Hello, welcome to lesson 2. We're going to go over the class starter now. And the question number 1 of the class starter is all about magnetic fields. Both magnetic fields produced by permanent magnets and magnetic fields produced by wires carrying current. So let's look at the assignment. Here it is. And the first one is about a wire carrying current. And you can see here, this arrow indicates the direction of current. Now, when you see an arrow like that, that's going to be conventional current. And remember, even though it's not the way it actually works, conventional current is how positive particles move in a wire. Now, we actually know that real current is electrons moving. But back in the day, when they were researching all of this, they had assumed that conventional current, or that current, was the movement of positive particles, namely protons. And so all the rules in physics are made based on that. So even though it's wrong, we still use that method. Conventional current refers to the motion of positive particle flow. What that means in this wire, positive particle flow is flowing upwards to the top right-hand corner of this wire here, along this wire. And that would mean real current, or electron flow, would be in the opposite direction, right? Positive particle flow is obviously opposite to negative electron particle motion. All right, so we solve these questions using, here's my wire, okay? And current was going in this wire in that direction like this. And we're going to use something called the right-hand rule. The right-hand rule indicates the direction of current around a conductor carrying current. Sorry, the direction of field around a conductor carrying current. So that uses this, okay? So my fingers are the field lines. My thumb is the direction of positive particle motion, also known as conventional current. And that is going to be aligned upwards along this wire like this. Notice the way my fingers wrap around the wire. They wrap in this direction, meaning that this wire carries a field that wraps this way around the wire. In other words, this way around the wire. Okay, so we're going back to our diagram again. Here we are. And if you grab that wire, pretend like with your hand, pretend like you're grabbing that wire on the page, wrap your fingers around that wire. What you'll notice is the field lines, or your fingers, wrap in this direction around the wire, right? That way. So the magnetic field around this wire comes out from the back, around over the top, and disappears back around the back again, like that. That's the magnetic field around that wire. Okay, so there's my diagram of the magnetic field around that wire carrying current as according to this, right? The right-hand rule. Thumb indicating direction of current, fingers indicating direction of magnetic field lines. So the red lines here are magnetic field lines. Now on the next one, we have a permanent bar magnet. A permanent bar magnet has a permanent magnetic field. It's not dependent on current or anything like that. It's always there. And magnetic field has directions, as you can see from the arrows in my first diagram. The direction will always be according to what way a isolated North Pole would get pushed. It's very similar to electric fields in that in electric fields, it's which way a positive test charge would get pushed. In magnetic fields, it's which way a isolated North Pole would get pushed. So a North Pole would get pushed away from this north side of the bar magnet and would get attracted to this south side of the bar magnet. So the magnetic field would look like this. It would get pushed away from the north and attracted to the south. the magnetic field lines look like this. So you can see that in and around the areas around the bar magnet ends here and right here, there's a high concentration of magnetic field lines, meaning the magnetic field is very strong there. Out here in the middle of the bar magnet, these field lines are far apart. They're not very dense, and so the magnetic field here is weak. Strong here because there's a lot of field lines crunched in a small area. Strong here, weak here, weak here. Okay. Okay, so the next one is a wire that's been bent into a loop. So you can see here's the current here coming out, which means the current must be going in this way, right? And so all we've done is we're going to take this loop or this wire and turn it into a loop. So I'm going to do that now. Take my wire and I'm going to bend it into, well, it's harder than I thought, very stiff piece of, bend it into a loop, kind of, ish. There's my loop, right? Now, in the same way, the straight wire has magnetic field lines that wrap around it like this. The wire carrying current bent into a loop has magnetic field lines that you grab the same way. So let's say, here's my loop. I have current that runs conventional current again, positive particle flow. Current that runs this way, goes up through here, around, and then out that way. Okay, so like this, and then out. So current is this way. Now, magnetic field lines as the current runs along the bottom here, current's running that way. So I'm going to put my thumb that way. I'm going to wrap my fingers through the loop like this as I grab the bottom of the loop. You'll notice that that has magnetic field lines running this way towards me, that way through the loop, or that way if I turn it this way, right? Now, on the side over here, the current is going upward. So my thumb goes up, I wrap my fingers through the loop, I grab the wire, and then again, magnetic field lines are pushed this way towards my face. On the top, current is running that way. So my thumb goes that way, and I wrap my fingers through the loop. Again, field is pushed this way. And on the bottom, current is running down here, or in the side, current is running down. So my thumb goes down, and I wrap my fingers through the loop, and yet again, field is this way. So at all locations on this loop, as the current runs in this direction, it pushes a magnetic field that way through the loop. This loop is one way of very strongly creating electromagnetic field, right? Because look, everywhere along this loop pushes a magnetic field in that direction. So they all add up to make a very strong magnetic field this way. All right, let's go back to our question. Here, so current is running this way through the loops and out. So if you grab any one part of any of this loop, you'll have current that runs, and let's take this part here. Current runs this way. And if you grab your hand and grab that part of the loop, you will see that magnetic field lines will run up, out, around, and back in, like that. Okay, same thing over here, right? It's going to be up, out, around, and back in, that way. And here, magnetic field lines are running towards, or sorry, current is running towards us. So the magnetic field is this way, up, out, around, and back in, like that. Now, this creates a donut-shaped magnetic field. As all these various points around this loop produce a magnetic field that's up, through the center, around over the top, down and under through the bottom. That's going to create a donut. Okay, imagine all of these together. That will also make a very strong magnetic field in the center. Okay, so there's my magnetic field drawn, not particularly very eloquently, but drawn on my diagram. So in the one below it down here, this is exactly the same. It's just more loops, which means an even more stronger magnetic field produced through the center. You can see this wire is wrapped around something. Maybe it could be an iron, a piece of round cylindrical iron, and that'll make this iron core very strong in the magnetic field. Or in this question over here on the very last one, it could be just an empty hole, like it was here as well, right? But you can see that the current is indicated with these arrows. In this arrow, it comes in from here and goes in behind, comes up around the back, down around the front, up around the back, down around the front, up around the back, down around the front, and so on. So what I always do is I grab this portion right here. See that arrow? I'm going to grab that arrow with my thumb pointing down. I'm going to grab that piece of wire. So there's the wire. It's like this. Here's my loop. There's loops arranged like this. So I'm going to grab the portion of the wire that's closest to me downwards like this. My fingers go through the loop like this. And you can see that magnetic field lines here will run on the inside that way. It'll then come out around and go in there. Same thing on this side, it'll come out, around, and go in there. Now this magnetic field here, running through this solenoid with several loops in a row is called a solenoid, should remind you of this magnetic field of a bar magnet. So the bar magnetic field and the solenoid magnetic field are similar, right? If I did it more neater, there, there. Direction always on those arrows, right? This one's a little different. The magnetic field, look at where the wire is coming to positive particle flow here. These are positive side of the battery is coming up this way. And so it's going up, up across the front and down around the back. So once again, we're going to grab our wire. Here's my loop facing me like this, okay? It's going up along the front, so I'm going to grab my wire and it's going to, the magnetic field are going to wrap this way through it, okay? So in this one, we have magnetic field lines that run slightly differently, like this. Right? I guess. Like that. There's the magnetic field around that one. Okay, now, lastly is this one here. This one is, what you see is a little circle and an X in it. We represent these ones like this. A little circle with an X, okay? Now, what that means is, what you're looking at is the end of the wire, like this. And the X indicates the back end of an arrow. So the arrow is running away from you like this, okay? And that means current is running away from you in that piece of wire. So if current's running away from you, right hand rule, right? Thumb goes away from you. Look at the direction in which the magnetic field lines wrap around that wire, this way. Okay, so when you do that here on that question, looking at your piece of wire like this, away from you, wraps around, you have a magnetic field that runs in this direction. Should be a circle. Now let's try again, make it a circle. Better. Okay, around the wire carrying current away from you. So the second one would be like a bit farther out. So, right? So magnetic field lines drawn around permanent magnets, like this one, a wire carrying current, like this one, a loop of wire carrying current, like this one, a whole bunch of loops, like these two, called solenoids now, okay? And then a single wire carrying current again. All right, now let's go down to the second page here. A charged particle will experience a force only if something inside a magnetic field. Well, that is only if it is moving. Inside a magnetic field. That's a very strange situation, unusual, that the force can only act on the particle if it's moving. If it's not moving, no force. Okay. Question 3. In a diagram below, the direction of force, describe the direction of force on a particle, the electron or proton that is moving inside the magnetic field. Okay, so let's first put in the magnetic field. We know that magnetic fields run north to south because it's repelled by the north and attracted to the south. Okay, so I'll put them in as red. That's the magnetic field between these two magnets, the direction of the magnetic field, and north to south is this way. Right? And now we have this little proton in this case, and over here an electron. This proton is being injected into this space where the magnetic field is. And so a moving charge in a magnetic field is going to experience a force. Now we have a different right-hand rule to describe the direction of that force. It looks like this. These fingers are the field lines. This thumb is the velocity of the positive particle. And my palm will face the direction of the push on the particle. Okay. Unfortunately, you're not sitting in front of me, because if you were, I would take a permanent marker off my desk, go down the rows, and literally write magnetic field here, force here, velocity here. It would be on your hand for like 4 days, which pretty much ensures you're going to remember it. But you're not here. If you want, you can do that to yourself now. So in the first one here, the particle velocity is downwards. That arrow indicates direct velocity, and the magnetic field lines run this way. So what we're going to do is align our hand to that diagram. Okay. Now I'm going to switch over to this and hold up my, oh, there's a shine there, and hold up my screen here. So field lines run this way, right? My fingers have to go this way. Oh, it's hard to do. Let's try that again. My fingers will line up with the field lines. My thumb will line up with the velocity of the positive particle. So from north to south this way, velocity of the particle is this way. This positive particle is going to be pushed downwards. Okay, so let's go back to that. Fingers point this way, okay? Thumb points this way. And so that'll cause fingers point this way. Thumb points towards me. That'll push downwards. Okay, maybe I can do it on a piece of paper better. So in this case, which direction is the particle being pushed? It's being pushed into the page, downward into the page. Okay, let's look at this one. And this one, the field lines are running up, okay, towards the south pole at the top. Now, the velocity is this way. However, it's a velocity of a negative particle. And the negative particle would always travel in the direction opposite to the direction a positive particle would travel. So let's change the direction of the positive particle this way. Field lines still run up towards the top of the page. You can put it on the page like this. Field lines run up. In my perspective, the particle velocity, positive particle velocity, is going to go to the right. And which way is my palm facing? Upwards. So this particle is going to be pushed out of the page. Okay, so that's the direction of the force on the particle as it enters the magnetic field produced by bar magnets. Okay, one more question. Question 4. In the diagram below, an electron is traveling with the velocity of blah at right angles to the magnetic field. So you can see the electron is traveling this way. The magnetic field is this way, upwards towards the top of your page. So fingers should be aligned upwards to the top of your page. The thumb should be in the direction of the positive particle. If an electron would go this way, a positive particle would go that way, the opposite direction. So notice my thumb points the opposite way of the red arrow, which indicates the direction of the electron. And my palm is facing upwards. So the direction is out of page. Okay, now we can also, that's B, part B. What direction will the electron be pushed when it first enters field? Out of the page. Part A, we have an equation. The force on the electron is determined by 3 things. The strength of the magnetic field, which is measured in Teslas, which they gave us in the question. It is 8.88 times 10 to the -5. Oh, that -5 should be raised in the question. It's not. But anyways, times the charge on an electron, which you all know is 1.6 times 10 to the -19, times the velocity, which they gave us in the question, is 2.55 times 10 to the 6. Okay, calculator. Turn it on. 8.88 times 10 to the -5 times 1.6 times 10 to the -19 times 2.55 times 10 to the 6th power equals, equals a mistake. Where did I make my mistake? Times 10 to the 5. Okay, try again. 8.88 times 10 to the -5 times 1.6 times 10 to the -19 times 2.55 times 10 to the 6 equals, got an answer this time, yay, 3.62 times 10 to the -17 newtons. Now, that may seem like a really small amount of force, but think about it. We're talking about the force on an electron, 9.11 times 10 to the -31 kilograms. So that small amount of force is going to cause some relatively significant change in the electron's direction, and it's going to start pushing it up. Okay. All right. So that's the class starter.